C'est bon? Ah, parfait. Just in time for the pointer.
Ok, voilà.
Thanks. Merci beaucoup. All right, so my first talk is about Pinsker inequalities, and more specifically the role of Marcel Paul Schützenberger for Pinsker inequalities. It's like a historical talk at some point, and also like an overview of what is called, it is very well known as Pinsker inequalities. All right, so the basic question that I will be dealing with is how far is one distribution to another? So we have many possible answers. Either people are preferring like distances, defining a metric, or divergences. We have many types of divergences, many types of distances. And for this talk, I will be only focusing on the most basic quantities, which are total variation or statistical distance, delta, and Kullback-Leibler divergence d of PQ, also known as relative entropy. So these are the definitions. These definitions include the discrete and the continuous case depending on the choice of the dominating measure. So it is well known that, like, for example, delta lies between 0 and 1, total variation, because of the 1/2 factor, and equals all quantities equal 0 if and only if the two distributions coincide. However, delta is a distance. Hopefully, it's rated to the L1 distance, but D is not. Delta is 1 if and only if the two distributions have non-overlapping supports, and in this case, the divergence goes to plus infinity, so it's unbounded. In a binary case, you have some like simpler expressions. For Bernoulli distribution, delta is just the difference between the two parameters. There's also some alternate definitions which are really interesting. When you consider a supremum taken over all possible partitions over the entire space. And so you can define delta as being what is classically known in mathematics as the total variation of the sign measure P minus Q. And similarly, divergence can also be expressed as the similar expression here. And so there has been a lot of work, very old work in the 1950s and 1960s about these quantities, and especially we know that it's enough to consider intervals when the omega is typically R. This is Dobroschin's theorem for divergence. It's also very easy to check that it increases by subpartitioning, and therefore the supremum is actually a limit for fine and finer partitions. And we get the well-known formula. For delta, it's already known for a binary partitions, which I call the binary reduction property, which will be useful in the sequel. And for D, it's the content of the Gelfand-Yalom-Perez theorem back in 1959. So all this is supposedly well known. And so we have the two nice properties about delta, one for delta and one for D. For delta, we have this binary reduction property that I mentioned. That is, delta is already attained for binary partitions, and therefore we have this simple formula here. Let me see if the laser is working. This one, okay, which implies that if delta is sufficiently small, then there is no statistical test that can be used to effectively distinguish between the two distributions. So it's that's why the total variation distance is probably the most used in many areas, for example, in computer science. However, for Kullback-Leibler divergence, we have another very nice property, which delta doesn't have. It nicely tensorizes for products of probability measures. And that is very especially interesting when you, I will give an application. So summary of properties. Okay, on one hand you have a metric, on the other another metric. On one hand you have a bounded distance with binary reduction, which you don't have on the other. But on the other hand you have nice tensorization. Okay, so the Pinsker inequality is about trying to connect the two and ask the question which topology is finer. And Pinsker inequality would take this following form. It's a lower bound on divergence as a function of the total variation distance, okay? Where phi is typically increasing and convex, like in the figure. And so this means that if divergence is small, then delta will also be small, and therefore the kind of topology defined by divergence is finer than the one defined by total variation, which was the basic classical result of Pinsker. And also, using binary reduction, it is very easy to see that it is enough to prove Pinsker inequality in the binary case, because delta can also can already be defined for binary partitions, and D can only increase by subpartitioning. And therefore, to prove in a binary case is simply a very simple expression. I will give that later. First, let me just give a very small example. Why is Pinsker inequality useful? Suppose, for example, that I have two coins. One is fair and one is bent, like unfair coin. And I would like to make the distinction between those two by doing n tosses. You are not allowed, of course, to look at the coins, but you're only allowed to look at the results of the n tosses. And for that, to be sure with probability 1 minus epsilon, you need that delta between the product of the distributions is at least 1 minus 2 epsilon. All right, the problem is that delta does not tensorize for the product of this distribution. However, divergence does tensorize, so we have to make the connection with between the two, and that's a content of Pinsker inequality. So by Pinsker inequality, you easily get a computable bound on the minimum number of tosses to actually be able to distinguish with some probability 1 minus epsilon. So so you have many other examples in the literature in computer science, which explains why Pinsker inequality is so useful. All right. So to summarize, find the best Pinsker inequality is find the best function phi, so that this inequality holds for any parameters p and q between 0 and 1. Which seems like a very simple exercise, but it's not, right? So I will just make a historical review of this. So the classical Pinsker inequality takes this form, d not less than c times the squared of delta, with some constant c, which the best constants being c equals 2, that we know already. And this comes from Pinsker inequality. But in Pinsker's book, as you can see in Russian, it took this special form. As a matter of fact, I found that Pinsker did not explicitly state Pinsker inequality, but not even in the general form. Instead, he proved two different inequalities, very involved proofs, and which combine give this inequality. And now, doing some maths, it can be shown that it's indeed gives a classical Pinsker inequality, but with a very suboptimal constant instead of the optimal 2. All right, so what happened then? Well, the first publication of an explicit occurrence of a Pinsker inequality was made even before Pinsker's book, but referring to Pinsker, Palvolinsky and Rozanov, which proved this, which is suboptimal, but still it's the first occurrence of Pinsker inequality. Then later in 1964, the first occurrence of the classical formulation of Pinsker inequality was in a book by a Japanese researcher, Sakaguchi. But unfortunately, this book was never published. So the first published occurrence of a Pinsker inequality of the classical form was by McCain, 1966, with suboptimal constant. And finally, Caesar mentioned the classical inequality with the optimal constant, but without proof. And it's only in 1967, 1 year later, that he actually proved this in a publication. And this can be written as a one-line proof using first-order Taylor expansions, like shown here. All right. However, the story is not over. Okay. First, Kemperman, 1968, apparently derived and independently the same inequality. But also, Caesar mentions earlier independent derivation of Kullback, 1967, which is even better because it includes a second order term in delta 4. All right? However, the constant of the second order term appeared to be wrong, and this was discovered by Vajda in 1970 and had to be replaced by the optimal constant 4/9 instead of 4/3. So what happened? Actually, what happened was that Kullback copied an earlier derivation in a French thesis written in 1953 by this guy, Marcel Paul Schützenberger, which I would like to talk about a little bit because he's a very interesting character. Okay, so Marco Schützenberger was actually from an Alsatian family, so his grandfather was a mayor in Strasbourg. Strasbourg is my hometown, and is well known for a beer, well known in Alsace, Schützenberger beer, which comes from the same family. Then his grandfather is also well known, Paul Schützenberger. He's a renowned chemist, which worked with Pierre and Marie Curie, and is well known to be the character of Les Palmes de Monsieur Schütz, which was a theater play and a movie after that. So Marcel Paul, during World War II, he was interned in a psychiatric hospital. He was active in resistance activities where he worked for the intelligence service. And he also published his first mathematical paper in 1943 on group theory. And then just after World War II, he known to participate in some Dadaist movements with Boris Vian. And he was also the main character in a well-known novel of Boris Vian, which is a well-known writer, French writer, as Dr. Marcus Schützenberger. And he was also a member of a communist minister, Charles Tillon. He published articles in lattice theory and in physiology while studying some exotic language. And he defended his doctoral thesis, so a medical thesis, on the contribution to the study of sex at birth, which was awarded by the French Academy of Medicine. So he was a medicist. He also applied statistical method to the analysis of various mathematical problems. He's one of the contributors to the discovery of trisomy 21. And in 1948, based on his statistic, a well-known psychologist, Anne Ansley, was giving a presentation, and from that statistic, he was offered a position in London, and then he went to London, and he said he would be better paid if he were married, and therefore he got married immediately in London with Anne Ansley, and this is actually a photo of their marriage. Okay, and finally he declined the position, and the couple divorced 1 year later. He was still publishing papers on combinatorics, on biostatistics with Georges Darmois. He was also a consultant of the World Health Organization, which sent him to Asia to combat infectious disease in tropical countries, in particular Indonesia, where he met his second wife. So, so many things happening for this guy, right? And it's not over. In 1952, he came to information theory, published his first paper on information theory, from biostatistics, and he defended his mathematical thesis advised by Darmois and with the President Fréchet on a contribution of the statistical application of information theory. And from this thesis, he was invited by Claude Shannon at MIT, which he spent the year 1956, 1957 there. And so he did many other things, like invariable length code. He's known for automata theory. He's known for the clean Schützenberger theorem, and for so many things. All right. Very interesting character. Now, coming back to his thesis, this was what his thesis contained. It actually contained Pinsker inequality with first and second order, and that was 7 years before Pinsker. All right. So, and this is D was, for him, was the difference between P and Q, so it's actually our delta, and W was the Wald information, as he called it, which for now is the divergence. Kullback library divergence. So he actually published this 7 years before Pinsker. And so what happened with the constant 3/4 and 3/9? Well, I investigated this in detail, and I found that most likely in 1953, the original French manuscript was in error, had the wrong constant. And then there was Cambo and Kotz who published a paper by copying a Schützenberger derivation verbatim, but without mentioning the original reference and without correcting the error, of course. And finally, Kullback also mentioned Schützenberger's word, but with the wrong constant. And finally, Kraft discovered that the constant was wrong and corrected to 4/9. And so Vajda was the one who pointed that the constant was wrong in Kullback's paper. And so he said that Kraft corrected an inequality of Schützenberger on which Kullback's result was based. And this was acknowledged by Kullback in the same year. And then later, Schützenberger apparently corrected his manuscript by hand from a 3 to a 9, because this is the 9 that appears in his thesis, and actually the 3 should has this form, and he apparently corrected by hand with a pencil. Okay. All right. So this is the story about the wrong constant, but still, Schützenberger derivation is correct and gives the optimal first and second order terms of Pinsker inequality, and even more than that. Kraft and Schmitz used Schützenberger identity to derive the third order constant, which was 2/9, which was converted to a Pinsker inequality by Toussaint. And much recently, Topso find that the best optimal constant in order 3 was 32/135. And even the third order constant, and all this used Schützenberger identity. So the thesis, the 1953 thesis of Schützenberger. Okay. Now, what happened next? Well, there was some more recent improvement of Pinsker inequality, which were needed because the classical Pinsker inequality becomes vacuous as soon as D gets large. The reason for this is that when delta approaches 1, then D should necessarily go to plus infinity. And therefore, we should, if we have a good Pinsker inequality, we should also have this situation, which it should also reflect that property. And so the first inequality of this type that was derived by Vajda actually has this property, okay, because of the 1 minus delta in the numerator. Then Bretagnol and Huber in 1978 had a simpler but weaker inequality, which is well known in statistics, and which appears in Sebakov's classic book. However, even a weaker version. And finally, the best known inequality of this type was derived recently by Gilardoni. And if you want to have a simple proof of this, you can look at my paper. But now the story is not over yet, but because we have the optimal. However, the optimal was derived in an implicit form and not explicit. So parameterized form. So this was derived by Fedorov, Hermos, and Topso by Fenchel transformation and with hyperbolic trigonometric function. So I have found a simplified proof and a simplified formula for this implicit form of optimal Pinsker inequality that you cannot beat. It's actually the correct function, which doesn't need to appear in explicit form. So if you want to have a simple proof of this, you can still have a look at my paper. And so to summarize, that's about all the Pinsker inequalities we know about. This was Bretagnol-Huber, this is Vajda, this is Gilardoni, this is Pinsker, and this is Schützenberger, which I talked to you about. If you have any other question, if you'd like to break the record, you just have to find the best explicit function phi, which satisfies this inequality. So it's up to you now. Thank you. If you have any question or comment, if you don't, then we get, yeah, please.
Is there such a rich history for the multivariate case beyond binary? Or it's...
So that works for any case. By binary reduction, you can always restrict to the binary partition. So it doesn't entail any lack of generality. Yeah. So and in fact, Schützenberger did it in the binary case only. But as we saw, this is not a restriction, in fact, for this case. And probably all this could be easily generalized, or more or less easily generalized to other types of divergences, other types of distances, and other types of Pinsker inequality that we can derive this way as well. Any other comment, question? Yeah.
Can these be generalized to F divergences? Any idea of whether these things can be elevated up to getting bounds for F divergences and things like that?
Yes, definitely. There has been some work done on F divergences, especially F divergences. F divergences also satisfy this binary reduction property, and there has been some papers as well. So there are some special cases of F for which the divergence is symmetric, and then you can find an explicit bound. But for other types, like the classical case of Kullback library, apparently you cannot find an explicit bound. Let's thank me again.